Okay, thank you. As I said, welcome to this workshop, the seamless ensemble and the simulation tool IT training workshop online, which will see us work together for the next 4 hours. First, some presentations to introduce the tool, and then some practicals. We will be working on the computer. I would like to invite you to switch on the cameras, at least for these first minutes, so that we can see each other and maybe take also a screenshot. Me, I was the first without video. My apologies. So that we can take a screenshot and see who is attending this meeting. Jon, can you go next slide, please? I will steal very few of your time just to introduce the two organizations who are co-organizing this workshop. The first is the Marine Ecosystem Analysis and Prediction Task Team of Ocean Predict. Ocean Predicts is an international global organization that promotes the development and use of operational systems for analysis and forecasting of the global ocean. In particular, the MEAP task team, it's the team of Ocean Predict with the mission of advancing the underpinning science and tools for integration of biogeochemical and ecosystem models into operational systems. The team is composed by 30 members across 21 institutes, which are spread across 12 countries worldwide. I am one of the two co-chairs here at Mercator Ocean in France, and the other co-chair since yesterday actually is Liu Qian Yu from the Hong Kong University of Science and Technology, Guangzhou, who took the place of Marjorie Fredericks from VIMS, who anyway will be with us in the co-chairing in this transition period and then part of the group again. Patron is Paul Di Giacomo from NOAA, USA. And you can find a better description of what is our activity in the link to the website and to the paper by Katia Fennell et al. 2019, which describes what is our focus, our targets, our remit. This remit is operational oceanography in a broad generic sense, which involves simulations in hindcast, reanalysis that assimilate data, short-term and seasonal forecasts, climate projections and scenarios, all types of simulations that we are interested in. Next, please, Jon. And the applications of these developments and these simulations are carbon cycle research and carbon accounting, and marine ecosystem health and productivity for a series of applications that goes from fisheries management to design MPAs to develop data simulation systems for biogeochemistry in collaboration with the other task teams of the Ocean Predict, in particular data simulation task team, for example. Next, please. The other co-organizer of this project is the Seamless project, of which I will give a short overview. The mission of this Horizon Europe project is to improve the operational simulation of indicators related to climate impact, marine food webs, and stakeholder needs. And some key facts about this project. It's an Horizon 2020 project that answered the call for the Copernicus Service Evolution. Copernicus is the European program that aims to develop information for citizens in Europe and worldwide by using a constellation of satellites of the Sentinel missions, as well in situ data and models in an operational framework. The duration of Seamless is 3 years. It started in 2021 and will finish at the end of this year. Budget 1.5 million euro, and 6 partners from 6 European countries that you can spot on the red dots. But it's an international project in the sense that, for example, our advisory board members come as well from the USA. We have Peter Jan van Leeuwen from the Oregon State University, USA, and we have Katia Fennell from Canada, for example. apart other advisory members from Europe. And the interesting thing is that 10 investigators of the Seamless project are also part of Ocean Predict. And here comes this kind of strict collaboration, which inspired us to propose this workshop on this tool. Next slide, please. The Seamless project aimed to develop ensemble data simulation systems, and it follows these 4 research streams. Development of new ensemble generation and data simulation methods, and this work package, the work package carrying on developing this work is led by Pierre Brasseur at the University of Grenoble. To develop coupled assimilation of physical and biogeochemical data, led by Bertino at NERSC. Coupled assimilation of remote sensing and in situ biogeochemical data, for example, from biogeochemical Argo faults and from ocean color, to bring together this information into models to improve our reanalysis, forecast, and understanding of the system. And then coupled assimilation for joint state parameter estimation. So to estimate also those parameters of the models that are more or less known, and so ultimately aiming to improve biogeochemical models. So these are the 4 research streams of the project Seamless. Next, please. And so the ambition of the project was to make flow these streams into a tool that can be used by research students, anyone, for testing these methods and approaches for data simulation, focusing in particular for biogeochemistry, and the seamless ensemble assimilation. I'm not going to spend so many words because Jorn, Lars, and Karsten will talk a lot about it. But just to say that we developed this tool, next slide, please, with the ambition to create a tool, a reference tool for teaching, training, research, and applications in biogeochemistry modeling and data simulation. So we really would like to make this a shared, worldwide shared tool for these purposes. And here today, it will be for training persons that are already expert, but we had application of this tool for example, in a summer school for undergraduate. It was mentioned at this tool, but also for co-developers of operational systems. And we had a couple of weeks ago a training session at the Siemens General Assembly on the use of this tool. And this tool actually, it's alive. It will be continue to be developed by future projects. One of these is the Necton project, which is another Copernicus Service Evolution project, in which we will add new components to this tool. Next slide, please. With this, I have really finished my brief introduction, and I let the word to Jorn, Karsten, and Lars to really go on with the project. And again, I want to thank you, all of you, for coming and joining together today to work on this tool. Have a nice work. Jorn, please.
Thanks, Stefano. So we'll present here in more detail this ensemble and assimilation tool, and that's essentially the output of work by me, by Karsten and Lars. You see the names on screen. Karsten and Lars each will be talking about particular sections of the particular components of the tool later on, and can introduce themselves further at that point. My name is Jorn Bruggeman. I'm trained as a biologist, but mostly working in between biology and physics, and almost always on development of new tools. And I'll present here sort of an introduction to the tool, and later on we'll have a hands-on session that I'll present and partially supervise. The layout of this workshop will be that we present what this tool is about with slides initially. That will be potentially 45 minutes or so, where you get enough background to understand what the tool tries to do and what it should be able to do. And from there on, we'll take a short break and go into a hands-on session where we show on screen how you actually use the tool, how you set it up, how you use it. And from there on, we expect it will develop into people individually trying experiments, trying to customize the scripts and and the settings that we have. That's more or less the layout of today. Let me check if I can move on. Yeah. So the outline is to talk about this EAT tool, talk about the components underneath, because those are essentially more important and bigger than EAT itself. EAT brings them together. We'll talk about the features, the things you can do with it, and then we go into the hands-on part. So what it is, really, it's a flexible and extensible software package. It's not a tool that draws very much a predefined number of things in a particular order. It is more of a framework in which you can design your own data assimilation experiments, bring in your own types of observations, have a wide range of assimilation filters to choose from, to play with transformations of data. It's aimed to give you control. So that's the flexible and extensible parts, and you'll see later on what that looks like. It's aimed at data assimilation of physical and biogeochemical variables in a coupled sense. You can do only physics, you can do only biogeochemistry. Most people will do both at the same time. And it's done in a one-dimensional water column model. And it is very much chosen to be this way, in one-dimensional, to have enough realism to generate a proper environment, so temperature, light, mixing in winter, and stratification in summer, that type of thing. So you get a relatively realistic environment, but not at insane computational costs. We're not going for 3D here because we want a tool that can run efficiently even on your own computer, on a single workstation, and can be used for data assimilation. So it tries to find an ideal balance between sufficient realism in the model context and high performance we can run quickly. It's not a massive code base, as it says here. The code base itself, what we would call EAT, what was newly developed, is less than 5,000 lines. The key thing is that it brings together a number of open source packages that existed before EAT and were well established in their field. So for the physics underneath it all, we use the general ocean turbulence model, GOTM. That's the water column model. It simulates the temperature, salinity, development, the mixing of traces. It's focused originally at least on turbulence, and Carsten will talk more about that later on. We'll use the framework for aquatic biogeochemical models in EAT, which is a generic framework in which people have written biogeochemistry, a whole range of biogeochemical models that you can use. And for the data assimilation methods, it uses a parallel data assimilation framework, PDAF, that Lars will talk about in more detail later on. And the key thing is it offers a wide range of data assimilation algorithms. So we're not trying to develop a massive new tool that does everything from scratch here. We're really bringing together established components and putting it together in a way that gives you maximum power to try a whole range of data assimilation experiments. To give you a quick flavor of the structure of this, it's if you come in as a user, that symbolizes a user, you come into this wanting to run an ensemble of models, because you want to, typically we will look at ensemble-based data assimilation methods. So you want to run an ensemble of models that each differ in their state or parameterization or both. And we want, from the spread that we generate, we want to essentially find out how to best incorporate observations and adjust the state as we go on during the simulation. So we correct the states, accounting for the observations. Which means that when we don't run a single model, we run multiple models, an ensemble of models, typically. Although you can do variational analysis for people that are into that. So what we do as a user, we start up essentially one model for each ensemble member. And we'll see later in much more detail what that looks like and how it works. But that's conceptually what happens. And that model here, assuming you can see my cursor, that is the watercolor model plus the biogeochemistry. That comes as part of EAT, and that should be already on your systems. You've all got installation instructions beforehand. And anyone who hasn't tried them yet is still encouraged to try them. It can be done in a few minutes. It's just that we don't have time to troubleshoot today. So that's the GOTM FABM side of the story. Now, you control your entire data assimilation experiment through Python, and I won't go into it now, it will come later. And underneath it all, there's then PDAF for the data assimilation filtering. So that's where the library of data assimilation algorithms is. So these components are key, and they are much, much larger than anything you might have on the outside. Your own user scripts here, run scripts, plugins, they tend to be small, tens of lines, that order. And the wrapping that we do around Gotama and Pharmac is small. It's these three components that are key. And that's why we'll talk a bit about them in more detail now. Underneath it all, again, there are a lot of third-party libraries, and people that have worked a lot on clusters and HPC systems will be familiar with some of them, and they will know that it can be a headache really to set them up on any new system. So what we try to do for EAT is to make that really easy, and I hope that most of you have had the experience that you could install EAT either on Windows or Linux or on a Mac within minutes. And that's the whole aim of this. And underneath it all, you still get your MPI, your NetCDF, your BLAST, your LAPACK, everything. It's all there and ready to use. I'll hand over to Karsten to talk a bit about the general ocean turbulence model.
Yes, sorry. Yes, I'm Karsten Bolding, and I've been working with Jorn for like close to maybe 15 years now, and the collaboration has become more and more sort of tight to the degree where we now work in the same small company, both of us full time. And we have been in this seamless project, and one of the tasks was to sort of come up with ideas for this tool that could facilitate easier data assimilation for a number of different reasons, teaching and research and stuff, and still be sort of affordable from a computational point of view, that you could actually do it on your workstation and would not need access to a high-performance computer center, as Jorn already mentioned. So a data assimilation system comprises of basically three different components. It's you need a model. For that, we have chosen this general ocean turbulence model. You need some observations, and you need a filter that can actually do the data assimilation. The reason why we have chosen the general ocean turbulence model is, as Jorn also said, that it provides enough realism that you can actually use real observations to assimilate and see the impact on sort of real systems. Being a 1D model, of course, also have some drawbacks, and I'll return briefly to those later. Gotham, some of you might know it, but it's actually quite old. It is approaching 25 years of continuous development. I'd say we have not been equally busy all days during these 25 years on the development, but things have happened and things have been changing sort of during the entire period. And there's sort of a quite big user group, and there's also a group of developers that have sort of put time into it over these quite a number of years now. It started out as mainly being for comparing different turbulence closure schemes by Hans Burkhardt. He looked at the Melee Armada and the what's the name, the Epsilon model. And then it was sort of extended to include more and more turbulence closure schemes. When that was sort of done, it became more and more a full 1D water column model that is very highly configurable. And we look into how that can be used later on in the hands-on sessions. Some years ago, Jorn took the initiative to link Fathom, that will be described shortly, to Gotham. So within the physical model, you can run a large number of biogeochemical models, and everything is configurable at runtime. In the old days, and for those of you who have worked with Fortran, Fortran was typically initialized via nameless files. We changed that some years ago to a format called YAML, which is very easy to read. So that's an advantage. On top of that, there's sort of a number of different programming languages that can operate on YAML formatted files. With nameless files, it was mainly only Fortran. And it is an advantage in this new era of software, where you typically have sort of multi-language projects where you have maybe a front end, as we do here, written in Python, and some that is performance critical, written in C or Fortran. Again, for those who know about Fortran, the changes to the Gotham code was actually very small. So to the core part of Gotham, where all the calculations are done, no changes were done whatsoever. The only thing we did was that we introduced a new main function calling the initialize Gotham, integrate Gotham, and finalize Gotham, and adding to that some MPI routines, so we could exchange data between the different components of EAT. But basically, any further developments that go into Gotham itself will be immediately available in this EAT version of Gotham, because it calls the same routines as a library. The next one, please. So I said that Gotham is highly configurable, and the way it's configurable is that you have a core executable, and that executable is operated by environment or files typically. So you read in forcing and initial conditions and other things through files. Some of those can also be set as constant or even analytical if it's tides, for instance. But typically it is via files. The initial conditions that you need for all state variables can also either be set as constants, but again, typically for real applications, you would read them in via files, external files. So now we have sort of everything needed for the water, initial conditions and boundary conditions. On top of that, we need the ASI exchange, and typically for that, we calculate the ASI fluxes depending on the calculated sea surface temperature. That has some big advantages instead of using pre-calculated fluxes. So to do that, we need wind and air temperature, air pressure, humidity, and you can also add precipitation if you want to. It's not mandatory to calculate the fluxes, but you can put it in. And in principle, many different places will provide these data. If you, I guess that's not the audience here, but if you work with lakes, quite often there might be a meteo station at the lake where you can get the data from. But you can also get them from national meteo offices or whatever. What we have chosen, not chosen, but what we quite often use is the ERA 5 reanalysis project from the European Center for Medium Range Weather Forecasts. But as I said, it's not the only one. One of the good things about that is that it goes back all the way to 1960. And that it is homogeneous throughout the entire period, because they sort of rerun everything from 1960 up to now with the same model. So basically, you have an executable. That executable will do whatever is specified via the input files and the YAML configuration file. And the next one. I think, have you had that link sent out? If not, you should try and enter it into your browser if you can sort of have both the Zoom meeting and the browser window open. Collecting all these different data sources that you need in order to set up a full-blown Gotham simulation can be a little bit tedious. So some years ago, Jorn decided that he would use some of his previous skills to make a web interface where you can go in anywhere in the world and select a point and actually do the simulation for that, a Gotham simulation for that point. And that is what this iGotham is. If you enter with this key, you will get some additional things. I think I'll switch to my version of that right now. Jorn, you have to stop sharing, I guess. So can everybody see this now?
Yeah, that's fine.
If just one can, then I guess you can, all of you. So if you enter with this URL that I showed on the previous one, you can see it has this key, and this key means that this MEEP up here, you're logged in as MEEP for this workshop. By design, it has been kept very simple and straightforward. So the idea is that you go anywhere on the map and you click at a point. And when you click at the point, then something happens. It spits out the latitude, longitude, and the specific depth. But not only that, it actually also provides information of meteorology. In this case, the wind speed and the temperature. All the other ones are there as well, but that's just what has been chosen to be shown. And on top of that, you actually also do have the tides. And if you think about that you can do that for anywhere in the world, then it's actually acting quite fast. The data used for this are listed here at the bottom. And all in all, there is about 10 terabyte of data, where the meteor forcing is by far the largest one, but also the ESA SST with a very, very high resolution, and the ocean color data sets are quite big. So what is done when you choose any point here is that the position is passed on to sort of the back end, and the back end interpolates from these big data sets to the specific position you have chosen. And that goes for, as I said, temperature and salinity. That would be used for initial conditions. The meteorology would be used for air-sea exchanges, and the tides will be used to generate additional mixing by the bottom friction. So that would typically be more important in coastal areas or where it's not too deep. Okay, so it's possible to zoom in on this one, and so I go back to this one. You can actually see it is quite reactive. It actually goes quite fast to go through and find sort of all this information you need. It is prepared for sort of distributed computing, in the sense that there's a common way into it via this website, but the actual calculations are carried out on a number of machines sort of in the back. Right now, these number of machines are some quite old Linux machines I have standing here in my house. So please don't make any very long simulations for now. Later on, Jorn will give you instructions on how to download, because if 30 people start to run now and they run for 20 years, then the room here will be hot in a few seconds. Okay, so the idea is that you do this, choose a specific point, and then you can make a simulation by clicking down here on simulation. One thing to watch out for in general is that it is a 1D model, and 1D models are very good in places where horizontal gradients, and especially advection, is of minor importance compared to other processes. But if you sort of are interested in a site where you know that that is not the case, then a 1D model might not be the best choice. So basically what you do, you click a point. So now I do it in the middle of the North Sea, and then I click simulate. And then here at the top, you can see there's sort of a bar showing what is going on. And then here are the results. So we have simulated 1 year. The default year is 2022. And on top of the simulation, we have actually extracted data where we show the temperature as a Hofmüller diagram, the same for the salinity. Then we have the turbulent diffusivity, so a measure of the mixing. And finally, down at the bottom, we have a comparison between the simulated sea surface temperature from Gotham and the observed remote sense data from the satellites. The connection between the observed data and the model data is very, very weak, or weak at least, because Gotham as such have not used the observed sea surface temperature at all. We will do that later because that's sort of the idea about the data assimilation. To the degree that the ERA 5 reanalysis project have used the SST, you can say that there is a weak link because we use that for forcing. I think I'm not going to sort of search for a place where it would be very bad, but we could make one more simulation where it's actually, I think I'll go into the Baltic Sea, where the tides would have tides will have a much smaller effect. And I mean, if you sort of zoom into down to sort of the individual spikes in the sea surface temperature can actually be followed. I think I will stop here, and there'll be a bit more. Jørn will later on explain how you actually use this to download a complete Gotham setup that you will use for the data assimilation experiments. Yes, I think Lars is on. No, Jørn, you're on back on the stage.
Yes, thanks, Carsten. So we'll come back to this I got them thing later on, because that is the one way where we can quickly get you a physical biogeochemical model setup that we can play with. I'll talk a little bit about FABM, so about the biogeochemical component of this, and then Lars will talk about the data assimilation methods that are available for BDAV. So Gotham is a watercolor model, physics only. FABM is a framework for aquatic biogeochemistry that plugs into Gotham and can plug into a whole range of different contexts, including 3D models, to just provide the biogeochemistry. It's really aimed at that one function, and it is meant to be relatively lightweight. It just empowers people to write biogeochemistry quickly and in a sustainable way. So it's a framework that has been developed since 2009. It has been supported and is still supported by European projects in particular, and on occasion small other contexts. It aims at portability in the sense that you can write your biogeochemical code once and use it with a whole range of physical models. So you can run it in Gotham in a watercolor setup, but also in NEMO in 3D, in ROMS in 3D, in unstructured grid models like FECOM and Schism, in a box model that's 0D, or you can access it from Python. All the same biogeochemical code, so you don't have the hassle of every time taking your biogeochemistry and recoding it for yet another physical model. The other side of it is modularity, which means that you can, in principle, write your processes, specific processes in your biogeochemistry, as a separate module, which you can then easily share. And a typical example would be something like a carbonate chemistry system, which you can write once and then share among different ecosystem models that want to do carbonate chemistry on top of everything else. So it allows you to write your process descriptions once and put them together in different ways. For instance, you might write a phytoplankton module and create 20 copies of it with different parameters to build a diverse ecosystem. Or you just transfer the carbonate system to different people. These days it aims also at stability. So we are not trying to change the way the framework works all the time, at least not in terms of the API. The way it connects to biogeochemistry, the way it connects to physics is stable. It has been stable for a long time. And whenever we make small changes, they're described in detail, announced in advance, and we help as much as we can for people to upgrade. So it's really meant to provide you with a stable platform to write biogeochemistry. It is not doing a whole lot of complicated things when it comes to coupling across grids or time steps or parallelization or domain decomposition. All those things are left with the physical model if it wants to do that. So it's not, Fathom is not competing or overlapping with a number of other toolkits that people might be familiar with, like MCT or Oasis or ESNF. It's a Fortran code base, even though you can write your biogeochemistry almost in terms of the actual equations, and you don't see much Fortran. It's open source, documented and published, as it says there on the bottom. The concept is that the people that write biogeochemistry can focus just on that. So we separate concerns, that's what they would call these days concerns, so memory management, advection, diffusion, transport in general, input, output, all that stuff stays on the side of the physical model, in this case Gotham. And the biogeochemist can just focus on state variables, diagnostics, parameters, and locally getting the environment and providing rates of change. That's all you do in a farming context. It's all running in one process, so it's not a separate executable, it's not even a dynamic library usually. It just integrates completely with, in this case, Gotham, but just as well with Nemo or VCOM to just provide biogeochemistry. If you want to get into the equations, the nice thing to see is that if you look at a single tracer, then the side that comes from Fathom is small. We talk about sinking velocities and about sink and source terms and about surface fluxes and bottom fluxes, but all the transport, all that blue stuff there stays on the side of the physical model. If you're running in 3D, then it's the 3D model that handles the transport of the traces. Fathom just focuses on these green bits. They can be complex and many, many lines, but it's a very dedicated function there. It does not try to do anything related to the physics. It has grown over time, and it supports now a wide range of physical and biogeochemical models, not because we write links to all those hydrodynamic models and we write links for the biogeochemistry. Fathom is just a framework, that's what we focus on. But other people have written the link to Nemo, the link to HiCom, VCOM, etc. These are almost all managed by other people, institutes across the world. And just in the same way, the biogeochemistry here on the right is distributed over lots of different institutes that each do their own developments. URSUM, for instance, here is in Plymouth at PML, BFM is in OGS, eCosmo is in NERSC in Norway, etc. They're all at different institutes and mostly managed by different people. You can write ecosystem models, whole ecosystem models, and they're often used in the context of, say, climate models for the IPCC or operational models in Copernicus. But you can also write process models, so just a model for fish, or just a model for suspended sediment, or spectral irradiance, and you can combine those process models with your ecosystem to build new, more complex configurations as needed by applications or questions that people put to you. It's still funded, as Stefan also mentioned. There's Seamless, Necton, Ocean, ICU are all projects that fund the development of new physical couplers. These three here, new ecosystem models are being brought in, and new process models are being brought in, all in the the duration of the sort of coming 2 to 4 years, depending on which project, really. That's all I have to say on the Fathom side, and I'll hand over to Lars to talk about PDAF.
Yeah. Hi. Yeah, I am now. Can you keep sharing? So I don't have the slides prepared.
There we come.
For that.
Yeah.
Thank you. Yeah, about PDAF. Yeah, so I'm Lars Nerer. I work at the Alfred Wegener Institute in Germany and do, broadly speaking, data assimilation methodology, software applications, ocean, coupled data assimilation, biogeochemistry, and so on, more from the methodology view. Yeah, and the third component indeed is a parallel data assimilation framework. So PDAF, which, yeah, broadly speaking, it's a data assimilation tool or framework which you can use in an interdisciplinary way, basically meaning whatever model you have. It does not even need to be something from earth science. So as we know, we can do data assimilation as soon as we have a model and data. So you can use it for whatever you like. And then, yeah, what do we do? The original aim was ensemble data assimilation. So PDAF provides support for the parallel ensemble forecast. So a bit like what was described before, but actually GODAM itself had already a feature to run ensemble. So that feature we didn't need from the PDAF side, but PDAF does have this. PDAF then provides data assimilation methods. And the origin of PDAF is really from having a software to be able to study different data assimilation methods under identical conditions. And this is where PDAF came from. And nowadays PDAF, well, has these different solvers or different data assimilation methods, ensemble Kalman filters, particle filters, 3D VAR is in there, which are all then implemented and parallelized and fast. And then we also have tools for observation handling, for diagnostics. And it's really designed in a model agnostic way, so you can use it probably with any numerical model. And so it is coded in Fortran. And if you have like a Fortran code or a model or a C code, C written model or C++, then you can use it in this native way. We also have now a Python interface, which one can use, which is more for Python coded models. Otherwise, going native, like in Fortran to Fortran is a better choice. So you can couple it to a model. I come to a minute to what is basically necessary for this. Technically, it's a program library which you compile, which you link then with your model, and then it's some additional functions. And in the code package, when one downloads the full thing from PDAF, it's also that there are lots of templates that help you to implement a data assimilation case for, say, your model. Indeed, this is all prepared. Yeah, PDAF is basically, that's why parallel is in the name. It is originally intended to do large things, but it can also be used for small things where we would not even really need the parallelization or so, but it can also be used for this, but we also run applications on, say, thousands of processor cores. So it is a small application for this, but a very interesting one. Yeah, we have separation of concerns. Model development can go on independent from data assimilation developments, independent from observation developments, and also like covariances, which you then need for like 3D VAR applications, which can be developed independently. It's not a particularly new development. So we had a first release in 2004. Since then, we had continuous development of this code and various applications and various users. So it has a large user base, somewhat worldwide, with various models. And it's open source. It's also published. Open source, well, we have the PDAF website, and then it's also now rather recently also at GitHub. And releases, the last 2 releases are also at Zenodo archived, so that one can use these variants. Yeah, this is kind of this overview, general overview of PDF. Next slide, please, Jon. So what we typically do is we couple PDF into a model. So it is possible to run data assimilation, keeping the model separate from the data assimilation. Then you have a separate program for data assimilation. You run the model as many times as you like for the ensemble, and then run the analysis step. That's something which is done, for example, operationally at the Copernicus Marine Service for the Baltic. What we often do is that we couple directly into a model, and that is actually just inserting 4 subroutine calls into a model. We don't really need to go into the numerics, so it's really very small changes that are necessary to basically initialize. We change the parallelization for ensembles, and then we insert an analysis step. So basically, we modify the model to be able to simulate an ensemble of model states. So EAT can run an ensemble of model states, and then there is an analysis step, which is called at some prescribed intervals, then you can run the model as usual. That's also a bit like in EAT, you run the model with an ensemble plus additional options then for the data assimilation side. So the sketch is showing this for an example of ensemble size 40. So you initialize the ensemble, run it forward, then you do the analysis step, you collect the ensemble information for ensemble camera and filters because they need to combine ensemble information. Do the analysis step, go back to the forecasting, and then you can do cycled assimilation without ever restarting your model. The EAT setup, so this is when we directly couple into the model, this EAT, and Carsten mentioned this before. Next, please, Jon. So this is the setup that we have in EAT. We have a separate executable for the assimilation, and they are linked with MPIs. That's also an efficient way here. So the assimilation only runs on a single process, is a 1D case. And here we have this MPI coupling, so no direct insertion of PDF subroutine calls into the model code, but MPI communication calls for this link. That also gives a nice setup, and it is still very efficient. So we don't go through the Python for the communication at that point, but we do the MPI collection of the ensemble. And this is then the setup how we run now in EAT. Next, please. What we also need for assimilation, so when we run an ensemble, we have an analysis step, so the solver step where we assimilate the observation. PDF is completely model agnostic and generic, so we just work with state vectors, and PDF does not know what is in the state vector, so there is no physics or biogeochemistry really from the PDF view in a state vector. It's just a vector of values. So what we have is an interfacing between model fields and state vector that's fully coded in EAT. Then we need observation initialization. So observation information, values, coordinates, errors of observations. Coordinates here, it's just the depth information. If we have profile observations in EAT, in 3D would also be the horizontal longitude, latitude information. And then an observation operator is what we need. And there might be at the localization in 3D cases. At the moment, it's not yet in EAT's localization, where you basically need to know local observations and a local state vector. And in the case of 3D VAR, you need covariance information. So covariance operation, multiplication with the square root of a covariance matrix, the typical application. So this is control vector transformations. They are also there. And next, please, Jon. So they are also there, and they are prepared in EAT. They're actually, what we have in EAT is the observation handling is configured in Python. The covariance operations are in Python. So there essentially you can implement whatever you like. We have not coded something there since it's really case specific. The colleagues from OGS have done applications with this and implemented there covariance operators. Yeah, at the moment we don't have the localization. We discussed that might be a feature that is that would still be useful also to put in. There are applications where it makes sense. And the state vector setup is fully coded and configurable. That will be shown later, I think. That basically, again, from the Python side, you can say what should be in the state vector. Physics, biogeochemistry, parameters, all possible and configured on the Python side. Yeah, next, please. Just to, as a last slide, to give an overview of the, well, as I said, PDAF comes from this comparison studies of data assimilation methods. So we have various ensemble filters in there, and actually also ensemble smoothers. We have particle filters, nonlinear filters there. Generally, there is an ensemble OI mode, which is, I think, not yet in EAT. So, but in EAT doesn't matter. EAT is so fast, so you can run an ensemble. The ensemble OI would basically mean integrate one model and use ensemble perturbations, but it is so fast that you don't really need this. We have the 3D VAR schemes, which actually a development that we did at the beginning of the Seamless project. So that was a new development that was really funded through Seamless. Next, please. And one more. Yeah, so what we also have is basically these model bindings. This PDAF package come like MIT GCM and our RVCM of FESOM, finite element CIS ocean model or finite volume CIS ocean model. There is a coupling to NEMO also, which was now also development mainly through Seamless. And so this direct coupling with NEMO. We have toy models, and available in EAT at the moment are ensemble Kalman. Some of these ensemble Kalman filter flavors. So the perturbed observations, but also then the more modern ETKF and ESTKF filters and the 3D VAR methods. This is what is currently then available in EAT, which you can configure. Generally, as shortly mentioned, that there is now also a Python interface. Actually, EAT is also a particular Python interface. We have another Python interface done by Yuman Chen at NCO in the UK. And then there also community does, some of the community provides their models. There is also like the Schism ESMF development, so basically having an implementation, an ESMF compatible implementation for PDAF. So, and then these codes are also there, but here we focus on EAT. So on EAT, and this is for the hands-on, we will focus on the ensemble Kalman filters, since as said, covariance operation, at least for parameterized covariances, is not readily implemented, but this is something where from the user side, you would need to put something into the Python code. Yeah, I think that's all for PDAF then.
Great, thanks very much, Lars. I'll mention a little bit more about EAT features, but hopefully after that we can quickly go into the hands-on bit. The installation side of EAT you've mostly seen, but perhaps since we talk so much about Fortran, it's worth noting that we won't be looking at Fortran today at all. What we are using today is a pre-compiled package. That's what it says here, this pre-built conda package, where the physics and the data assimilation schemes and the biogeochemistry have all been put together in a prepared way, and you just install it. And you can use it, the way you use this through Python. So the only code that we will look at today is Python, and typically those are not too many lines. It's through Python that you configure your experiments, that you specify the observations, and it can be relatively quick. There's no Fortran today, although you can look at each individual code base that we talked about to see what is in there if you're interested. There are other ways to build EAT, and they each have their own uses. This pre-built package by definition means that there's a pre-built selection of biogeochemical models, and some biogeochemical models are distributed outside of the EAT context altogether. So people that have those models, those external ones, they can build their own version of EAT with their custom biogeochemistry included. There is a recipe for that there on the wiki. You can follow the link here if you want to know more. Similarly, when you're on a cluster on HPC system, you typically don't want to use this pre-built package, which brings in its own MPI and its own BLAS, its own LAPACK and NetCDF. You really would like to integrate as much as you can with your cluster environment, and In some cases, you have to when it comes to MPI. So there's a recipe for that as well. It's not the only way, the way we use today, but it is by far the quickest. So hopefully everyone has succeeded in installing it. We haven't had any issues reported actually. So presumably it works on all three platforms. So we're looking at Python code to generate your ensemble, Python code to run your actual experiment and configure it. And in the end, we'll look at Python code to explore the results, to visualize some outputs, that type of thing. And the very first step always in the context of a data assimilation experiment is to generate your ensemble. So as Lars said, we're looking at ensemble-based methods, typically ensemble-Kalman type methods. And the first thing you want is an ensemble of model states or configurations or both. That's different, with different values in there. You want some spread. You want to maintain that spread throughout the simulation. You learn from the model spread and you find out, the data assimilation methods find out how to best integrate the observations in there. To generate your ensemble, you can perturb parameters and forcing, so physical parameters and forcing that go into this one specific file called gotham.yaml. You can perturb your biogeochemistry, particularly your biogeochemical parameters in fathom.yaml. And we'll come back to these files later on. And you can perturb initial conditions, which is perhaps the most sort of classic way of looking at data assimilation, where you just start off with say a restart file, a single state, the end result of a previous experiment, and you take that single state, you perturb it, for instance, by applying an additional random scale factor to every value. And that scale factor is different for each ensemble member, so you generate a spread across states for where that each member starts from. Now this can be done relatively easily in EAT with a few lines of Python code. So this example here shows how you take in the relevant libraries, and EATPy is the only one that is ours, that is EAT. You set an ensemble size, then you say you want to take this physical configuration and you want to change, you want to vary a number of parameters, 3 parameters across the ensemble. In this case, a scale factor for the 10-meter wind in X and Y direction, so east, west, north, south direction. And you want to apply a scale factor to a background turbulent kinetic energy. That's called K-min in Gotham. So the way to generate scale factors is essentially standard Python. We use the NumPy library. We say it's a log normal distribution here, and we give it a spread. The median is always 1 for a log normal distribution. So you get some spread around the value of 1, and you apply that to the ensemble members. So you get, in this case, 20 different scale factors here. Here another 20 different scale factors. Here another 20 different scale factors. So each ensemble member will effectively differ in the X and Y wind speeds that they experience, and they will differ in the background turbulent kinetic energy that they experience. And here's a reference value being applied there. This 3 times 10 to the power minus 6. So it can be pretty quick to generate some spread in your parameterization. This is the physical parameterization, which includes forcing. In a very similar way, as we'll see later on, you can generate spread in your biogeochemical parameters. And in a pretty similar way, you generate spread in a restart file. There are example scripts in our repository that I'll point you to soon, but it's just to show that it's a few lines of Python to do the basic data assimilation tasks here. The other ingredients, as was mentioned before, is observations. You need to provide your observations that in the end will guide your state correction, the movement from a forecast state to an analysis state. The observations, since it's a 1D model, can either be depth dependent, so you might have profiles of temperature, or salinity, oxygen, or any other variable as long as it was measurable throughout the water column. So you have a series of time and depth, some observed variable such as temperature, and some uncertainty in that variable. Those 4 columns you provide in a text file, and those are your observations for this particular variable. If you have another variable that you observe, you have another file. So this is one for temperature. You could have a similar file for salinity, for oxygen, for anything else that you have observed. This would be the type of file you have if you take data from an Argo float. You can also have depth-independent information. The typical example of that would be remotely sensed information, such as sea surface temperature or sea surface chlorophyll. And there, it's pretty much the same format. It's still a text file. You just have 1 column less. You don't have depth. You just have time, variable, and uncertainty there. So the file formats are meant to be really, really simple. It should be easy enough to take observations in any kind of format and generate this type of text representation of the observations that EAT can then read and consume. When it comes to the model state, as Lars said, the starting point in EAT is always, let's take the entire state of the model, which means all physical variables and all biogeochemical variables. Physical variables include temperature and salinity, but also the horizontal velocities, the U and V components, and turbulent quantities. Biogeochemistry includes any biogeochemical state variable, and which ones they are depends completely on which biogeochemical model you have chosen. But it's worth noting that both pelagic and benthic variables are by default included. So that's a pretty comprehensive model state. In many cases, it's more than people would want to vary in one go. Many people would focus first on a subset of the model state that they allow the data assimilation filter to operate on. And that is, of course, supported. You can easily select a subset of this full model state and present only that substate to the filter. So if you're doing physical data assimilation, you might say, well, let's forget about turbulent quantities, let's forget about velocities, just focus on temperature, salinity, and update those two fields only. That's possible, and we'll see later on how. But conversely, you can also augment the model state to add more to it. One typical thing you might add to it would be diagnostic variables that you have observed. So a diagnostic variable in a model, such as primary production, might be measured, and that's not easy to do, but they can take bottles and measure primary production. If you have those observations, they would be valuable to correct the model state. So there's a mechanism to add any model diagnostic into the model state, so you can actually observe it and include those observations while you do data assimilation. And like I think Stefano, among others, mentioned, you can also add your biogeochemical parameters to the state and estimate in that way. So then the biogeochemical parameters, which used to be constant in time and space, become time varying. Not vertically varying in this context, but time varying. They essentially make a random walk in space, and the observations are used to estimate the current most likely value of each parameter that you expose that way. So this mechanism of augmenting the model state is used both for diagnostics and for parameters, which altogether gives you a lot of freedom to really estimate any type of observation you want and to estimate parameters. The data assimilation cycle is pretty much a classic one and very comparable to what Lars showed before. The key thing is that this model, so each bottom, the coupled physical biogeochemical model, stays running all the time. We don't shut it down and after to bring in the observations and calculate analysis state. The model stays running. Every time it receives a new time to time integrate to simulate to, that is the time of the next observation. The model will run until that point, send back its forecast state, and in the other process that handles the filtering here, that forecast state is being processed, in the end presented to the data assimilation filter, so to PDAF. PDAF then takes the observations and the model states and computes the analysis state that in the end is sent back here to EAT-COTM, which was just waiting for that to come back. So the processes stay up and running, nothing's shut down, there's no communication via files, it's all via MPI and memory, and therefore very efficient, as you will see. The one other thing worth mentioning is that there's these green things in between, these plugins, which are really very, very generic constructs or APIs in the code through which you get complete access to the observations, to the forecast state and analysis state. And at each point you have the ability to intervene, if you like, to overwrite either the forecast state or the analysis state or both, based on whatever information you gather from those states or from the observations or from parameters that you've specified before. So you're completely free there to modify states, and we'll see that it can have many uses. We'll come to the details about configuration later on. We'll show which files are involved and therefore which ones you might want to look at. So these plugins, the typical uses for them would be to check the state or modify the state, basically. So a simple one would be to say, well, that model state, the entire physical model state, let's just restrict that. Let's throw out most variables, keep only, say, temperature, salinity, chlorophyll. That is one example that we have later on. So limit the model state presented to the filter. That is one thing you can do in these plugins. You can transform variables, since you have complete control over the values. So you can transform into a Gaussian space whatever that may take, whether that is a log transformation because variables need to stay positive and are likely to be log normally distributed, or another type of transformation for variables that are constrained between 0 and 1. There's complete freedom there. You can apply any function you like, a custom one, a NumPy one, a Python one, and apply your own transformations. You have access to the state, so you can check whether the state is valid. And the basic thing would be to check whether there's not a number in there or not an infinity in there. But you can also check whether variables have stayed within their ranges. You can go one step beyond and say, well, if they go outside these physically meaningful ranges or biogeochemically meaningful ranges, we clip them back to their lower or upper bounds, just to ensure that they remain physically meaningful, and the model can start its next simulation from a physically meaningful state and therefore not crash. Or you can do tricks where the corrections to some variables are converted into corrections of the others, just to ensure mass conservation. There's really no limit in these type of tricks you can do. If you do variational assimilation, like Lars referred to, the 3D VAR, you can and you have to do more. You have to prescribe your background covariance matrix, and plugins are being used for that purpose as well. So plugins are a generic way to get, during your experiment in Python, access to what happens just before and after analysis. In the 3D VAR case, during analysis. It can also be used to save the ensemble state, since you have complete access, or to compute diagnostics of the ensemble state and save those. And there's examples for those as well. So these are typical uses, but the key thing of these plugins is it is very easy to write one. You can write a plugin with 5 lines of code. So people have taken the concept and done things with them that we never thought about before. Advanced uses, in this case, an example from Anna, who I think might be here among the audience, is that she took the temperature and salinity before and after analysis, converted that into density, and reconstructed the change in density proposed by a data assimilation filter. And based on the change in density, she computed nutrient corrections and applied those as well. So it becomes a mixture of almost variational and ensemble-based analysis that way. It's really a hybrid type of approach. You have complete freedom to put those things together any way you like. And of course, you're yourself at that point responsible for making sure that it all makes physical and biochemical sense. But the freedom is there. Ensemble generation was, 6, 7, 8 lines of Python. If you just want to assimilate a single variable, then that is a similar number of lines. So here, this is a run script where we assimilate only sea surface temperature. And the idea is pretty much as before. You just take in the EatPy library. You say that you're dealing with a Gotham model, so a watercolor model, as opposed to a box model or a 3D model. We specify which data assimilation method to use. So that's PDAF and the ensemble subspace transform Kalman filter. We select only temperature and salinity to operate on. So this is limiting the state presented to the filter to just temperature salinity. We say we have observations on temperature, and not throughout the water column, but just at the water surface, which in Gotham is the last index, so -1. Those observations are present in file ccisst.dat. That's it. That is the entire experiment. So we've specified which part of the state to operate on, we specified the observations, and then we just run the experiment. Underneath it all, there's a Gotham setup, which has physical forcing, which has its own parameters. Typically, there would be a biochemical configuration as well, and we'll all see what they look like. But when it comes to data assimilation, when it comes to EAT, this is all you need to do to set up an experiment. And that is enough to generate things like this. Of course, the analysis scripts come later, and we'll see an example of them later on. The sea surface temperature here for 3 years, you see the model is, particularly in winter, spring, is underestimating temperatures. That's the blue line versus the black observations. If you assimilate your observations, you get the orange line, and the model curve is lifted much closer to the observations. That's nice and expected just because you do data assimilation, but you can see that there are implications not just at the water surface, but throughout the water column. So this is your best new estimate for temperature throughout the water column, with depth and time. And here you can see that effectively what this does is it causes deeper mixing in summer as well as in autumn. So the mix layer extends a little bit further. You can imagine that, therefore, this assimilation of sea surface temperature has implications for biogeochemistry as well. This deeper mixing causes nutrient upwelling or upmixing. That has implications later on for the phytoplankton. In general, so we'll go into the hands-on bits in a second, and we'll be there to guide you, and we really encourage you to then ask questions whenever you have them or when you run into trouble. But if you want to know more about any of this, you can look at the code, which is available there at the top link. There's a user guide, a wiki, which is really detailed at the moment, and a good place to start. For instance, if you want to know more about the parameters you can use to configure your data assimilation method, or when you want to know more about your observation file format or how to write plugins. There is a report/draft manuscript that you can visit, where you can see some example applications, more advanced ones, for parameter estimation, for custom workflows and scripting around each, for doing 3D VAR in a particular way. And you can see the people behind those example applications there, and they would probably be the best ones to contact if you want to know more. I suggest we take a break, well-deserved break, 15 minutes if that's okay with everyone. Then we reconvene at 5:30